Number 56, we have a potentiometer circuit arranged in figure this. This wire AB is 600 centimeter long. At what distance from the point A should this jockey B touch the wire to get the zero deflection in this galvanometer? If the jockey touches the wire, that is the second part, will come to that. So here is what is happening. This battery B it makes a current flow in this circuit, and the whole distance between A and B has a resistance of 15R. So it will set up if you consider point B with respect to B, there will be some voltages divided from here. Let's say it's 0 volt here, at 1R will have some voltage, then it will keep increasing along this length. And then we have a battery here. The battery will have some voltage with respect to point B, because with respect to point B, point A will be quite high voltage, close to epsilon, and then this battery will have a smaller voltage that will reduce the voltage across it, and at this point and these 2 points become the same voltage, then there will be no deflection in the galvanometer, and we need to calculate this. There is one slight complication in this problem, is that we have an internal resistance small r here. The first thing we should do is try to find out the current flowing through this circuit, and that is given by I is equal to V divided by this 15R and R, or epsilon divided by 16R. Now we will take the I needed to find out the voltage at this point with respect to point B, because we need to make this voltage same as the voltage at D, both of them taken with respect to B. So the whole thing to try to solve this problem is finding these two voltages and making them equal. So the voltage at A with respect to B, first we need to find out the voltage at A with respect to B. This will be this epsilon from here, this point, this epsilon minus IR. The voltage at A and B will be reduced by the drop across this small resistance R. So that will be epsilon minus IR, and we know that I, the current flowing in this resistor, is epsilon by 16R. So it's going to be 15 by 16R. A little less than epsilon because of the small drop across this internal resistance. Now we know the voltage at A, we can find the voltage at C by taking this loop. There is no current flow in this loop because we have not yet connected C to anything. Because of this is open loop, there is no current flowing in this resistor now. So with respect to B, with respect to point A has 15 by 16 epsilon, we reduce this voltage by epsilon by 2. We get 15. Now notice that this battery is trying to send the current in this direction. This also is trying to send the current in its opposite direction. So we need to reduce this voltage by epsilon by 2. And then from here we get 77 by 16 epsilon. 7 by 16 epsilon here. So the point D also has to be 7 by 16 epsilon, so that if we connect anything between these 2 points, and they will be at the same voltage, and there will be no flow of the current to this galvanometer. So at point B we have 0, at point A we have 15 by 16, at somewhere in the point D we have 7 by 16. So we know that we can find out the point because it's linearly varying. And the formula is simple. We need to find out at what point D, what is the ratio of this distance versus this distance, which will depend upon the ratio of the resistances. We know that R1, if this one has R1 resistance, this one has R2 resistance, and the current flowing in this branch, I will be given by VAB divided by R1 plus R2, and this should be same as VDB divided by R2. And we know that VAB we have found out as 15 by 16 epsilon. Is 15 by 16 epsilon. R1 plus R2 is 15R, and voltage at D, we know this voltage at C is 7 by 16 epsilon divided by R2. That is what we need to find out. So from here, after doing all this cancellation, 16 cancel, and this 15 cancel, epsilon cancel, we get R2 is equal to 7R. We could have guessed this to be 7R because the voltage between these two is 7 by 16. The voltage across whole thing is 15 by 16. So this resistance has to be 7R, and this resistance has to be 8R. That is how these things get divided. R1 plus R2 is 15R, so R1 becomes 8R. Now we can find out this length. We know that this length divided by this length will be this resistance divided by this resistance. So we have L. If this resistance distance is L, then L divided by 600 minus L is equal to 8R divided by 7R. And from here we get 7L, and this one goes to the right, minus 8L. 7 minus 8L comes to the left, so 7L plus 8L, 15L is equal to 8 multiplied by 600 when 600 goes on this side. From here we get 15 into 4, so it is 40, into 8, 320 centimeters. Okay, so the next part of the problem is now if the jockey touches the wire at a distance 560 centimeter from A, what will be the current in the potentiometer? So as we move further from A, the voltage is no more balanced, and therefore if we touch this point to any other point, there will be a flow of current, and we are touching it at 560 centimeter from A. So when this one distance is 560 centimeter, this distance will be 40 centimeter, and in that case R1 plus R2 is 15R, and R1 divided by R2 is 560 by 40. 560 by 40 becomes 14, 1 times 14, 1, 6, 4, 4. So this is 14 by 1. So R1 divided by R2 is 14 by 1. R1 plus R2 is 15. So obviously R1 will be 14R and R2 will be small r. We know the ratio of these resistances. Now we have connected this jockey at this point, and we need to find out the current in this circuit. We can use simple Kirchhoff voltage law in these two circuits, and it should be possible to find out those currents. So this is what we have done here. We have set up the Kirchhoff loops. We assume that the current from in here flowing in this one is I1, and then let's say out of the I1 current, I2 current goes into this branch. So the remaining current, let's say, flows into this in this direction, I1 minus I2. So we can start creating two loops. One loop could be this loop, and in this loop the power supply is epsilon, and the current flows is I2 current flowing here in the same direction of the indicated, so the drop will be 14R into I2 into 14R. And then plus, if this current we have I1 from it comes here, finally whatever comes here, this returns current is I1 because that's the current flowing into this. So I1R plus I1R is 2I1R. That gives us the first equation. For the second equation, we can take this loop. Maybe it's better probably to take this loop. So you can do both of the things. Probably that will be better, but I have done it this way. So for this loop, we have epsilon by 2 equal to 14I2. Now when we do epsilon by 2, the battery is trying to make the current flow through this direction, and anything that helps it comes to the other side of the equation. Anything that opposes it will be negative. So this epsilon 2 IR will be equal to the drop across this in the same direction. So we have 14R into I2 here. And then when we come to this one, the current direction is here. This I1 minus I2 is the current flowing in this one, and its direction is trying to be opposite to that. So we get minus I1 minus I2 into this resistance R. And this one simplifies to 14I2 plus I2 plus I2 is 15I2 minus I1R. So this is one equation, this is second equation. We are trying to solve it for, let's eliminate I1. So multiply this equation by 2. So 2I1R and 2I1R, they get cancelled. 14 and then this is 14 and this is 30. So if we add these two, 14 plus 30 is 44. So 44 I2R is equal to epsilon by 2 into 2 plus epsilon 2 epsilon is 2 epsilon. Or I2 will become 1 upon 22 epsilon R. So we now know I1, I2, we can find out I1 by substituting it into one of these equations. We will find, going through this, I will not go into details, you will find I1 as 4 by 22 epsilon, and this, because the current we need to find out is I1 minus I2, that will be 4 by 22 minus 1 by 22 is equal to 3 by 22 epsilon.